So I think that the time has come. So we continue our lecture series today. And the first lecture is given by Charlie Groechenig. So everybody knows Charlie very well, I guess. So Charlie, you are welcome. The stage is yours.
Hello, everybody. Good morning, good afternoon. Thank you for the invitation. This is a good opportunity to connect or reconnect. And it's a topic that's dear to my interests. So this talk is addressed to sort of the novices, the people who are starting to learn about sampling and discretization. So the emphasis will be on simplicity. For the experts, it may be folklore, but I think it's worthwhile to start on a basic level. So the topic of the workshop is a perennial problem of processing data. You want to learn something about an unknown function f from its samples. So f could be supported on a subset in Rd or some manifold, and then you want to say something about f. Either you want to approximate f from the samples, or you want to approximate some integral from the samples. And actually, that's what brought me back to the topic when I visited Nick Trefethen at some point. He was wondering how all these error estimates for quadrature rules on uniform grids would carry over or generalize to non-uniform grids. And there I discovered my recent interest. You will hear a lot about optimal sampling strategies tomorrow. Currently, there's a lot of random sampling strategies, but I want to keep it basic. So the ingredients are very simple. You have a hierarchy of finite dimensional subspaces. Typically, these are polynomials. We have some way to measure smoothness, in our case, Sobolev spaces. Central topic is Marcinkiewicz-Zygmund families. Definition follows. We will need solution to least square problems. There's a component of approximation theory. And there's a link to other fields, say to PDE via the spectral function or orthogonal polynomials via the Christoffel function. What I want to, so when you look at current literature, it can be quite technical and it's on a high level. What I want to emphasize is the basic ideas are fairly simple. I restrict myself to L2 norms. And we start with a model case. So the underlying set with space is just the torus interval of length 1 with the endpoints identified. And the hierarchy of subspaces are just the trigonometric polynomials of degree n. So these are linear combinations of the exponentials up to degree n. So there are two ingredients. One is sampling sets, and another one is weights. So we think of these sets as, we think of this as layers. So the subscript n, will always refer to the degree of the polynomials. And now we have a sequence of finite subsets xn in the torus. We call that the Marcinkiewicz-Zygmund family. If I have a hierarchy of sampling inequalities for the trigonometric polynomials. So for each subspace, trigonometric polynomials of degree n, I have a sampling inequality on the nth layer of the Marcinkiewicz-Zygmund family. Okay, the n refers to the layer, and the k labels the points in the nth layer. So for trigonometric polynomials of degree n, I sample them with the points in the nth layer. I put in the weights, and the sampled weighted L2 norm is equivalent to the 2 norm of the function itself. Okay, so for each subspace of trigonometric polynomials, I have a sampling inequality. The main point is that the constants, sampling constants A and B, are independent of the degree of the polynomial. What plays a role is the ratio of B over A. That's kind of the global condition number of the Marcinkiewicz-Zygmund family. Now, before I move on, let me say something about the weights. When we started sampling theory, we considered that a minor modification that was practical to sort of get a better conditioning, but it has become more important. And one choice of weights would take uniform weights, so the dimension of Tn, trigonometric polynomials if the degree n is 1 over 2n is 2n plus 1. So you could just weight every point by 1 over n, or you could weight every point by the cardinality of the nth layer. What turned out to be quite useful in a sampling problem is to take for the weight the distance between two consecutive midpoints. So when the points are clustered densely, then the tau and k would be small. When you have large gaps, then this difference would be large. And so large gaps would give a large weight to a given sample. So let's see. So if you look at this here, so these adapted weights will sort of give different, so would compensate for local variations of the density. In higher dimensions, you would take the size of a Voronoi cell or whatever. I think in tomography, this type of weights has been discovered under the name density compensation factors, and there they also are used to get better conditioning. Another possibility would be to just count the number of points in an interval of length 1 over n and give that as a weight. So for me, the weights are given, but of course, in practice, you need to think about what to take for these weights. So now you're given let's see what's happening. Okay. So you're given a continuous function on the torus, and you sample it with points in the nth layer. Okay. So unless you have some information about the function, unless you impose some sparsity constraint, the best way to approximate f from these samples is by finding the least square approximation by a polynomial of degree n. So we try to find polynomial of degree n in such a way that at the samples, at the nth layer, the weighted L2 norm is minimal. So this is a least square problem. And so the polynomial Pn that we find by this least square problem is the trigonometric polynomial, degree n, that approximates the given sampled value best possible in the L2 norm. So the question is now, well, this is a computationally feasible problem, at least in dimension 1, in low dimensions. Problem is, what does this trigonometric polynomial tell us about the original periodic function? So in the sequel, I'll need the orthogonal projection of functions onto trigonometric polynomials of degree n. That's just the nth partial sum of the corresponding Fourier series. So comes the next ingredient from approximation theory. The underlying paradigm is always smoothness is equivalent to approximability. The simplest scale of smoothness space that we can take are the Sobolev spaces on the torus. So this is just a weighted L2 sum. The weight is basically some power of the index k, precisely 1 plus k squared to the sigma. So these are the Sobolev spaces. Just want to recall well-known and easy to prove facts. If the smoothness parameter sigma is greater than 1/2, then the Sobolev space embeds into continuous functions. So in that case, it makes sense to sample. There's a convergence rate both in the 2 norm and in the supremum norm. If you approximate f by trigonometric polynomial of degree n, both in the 2 norm and the infinity norm, then the order of approximation is n to the negative sigma plus 1/2. The sigma is the smoothness parameter. And the constant is some absolute constant depending on sigma and the Sobolev norm. What's more interesting is assume that you have a Marcinkiewicz-Zygmund family. Then you can also say that, the sampled weighted L2 norm for a function in the Sobolev space can be estimated by the Sobolev norm and some constants. And basically you just take out the supremum, and then you have the sum over the weights, and these can be bounded by the constant b in the Marcinkiewicz-Zygmund inequalities. Just if you take the constant 1 here, it's just the sum of the weights, and that's less than or equal to b. So these are 2 ingredients. I think now I'm already ready to state the basic theorem. How well can we approximate a periodic function in dimension 1 from samples that come from a layer of a Marcinkiewicz-Zygmund family. So the rate of approximation will depend on the smoothness, sigma, and the result is the following. If f is in the Sobolev space with smoothness parameter sigma, then f minus the trigonometric polynomial that's computed via least square approximation from the samples of f in the 2 norm decays like n to the negative sigma plus 1/2. So n is the degree by which I approximate. Sigma is the smoothness. The 1/2 is, well, somewhat artificial. And the rest, the constant is the Sobolev norm of f, is some absolute constants that comes from, say, Sobolev embedding, and is the condition number of the Marcinkiewicz-Zygmund family. If you start with a function that's super smooth, so that extends to an analytic function in a strip around the real axis, strip of width rho, then the approximation of f from its samples in the nth layer by a trigonometric polynomial decays actually exponentially, and the decay rate depends on the width of the strip. So this is a first answer to the question, how well can I approximate continuous function on the torus by given points from a Marcinkiewicz-Zygmund family. Now let me take the next step, and maybe we go back just to recall once more. Marcinkiewicz-Zygmund family is a hierarchy of sampling inequalities. So in particular, the samples of a trigonometric polynomial determine the trigonometric polynomial uniquely. You're in finite dimension, so you surely have a reconstruction. You have a dual family, a dual frame to reconstruct. Okay, so trigonometric polynomial of degree n can be completely reconstructed by its samples on the nth layer via some family of dual functions. Now integrate on both sides, okay, from 0 to 1. Then you see that the integral over p is equal to the sum of the sampled version of p on the nth layer times a weight, and the weight is obtained as the integral over this system of dual functions. So this gives us a quadrature rule. We sample f on the nth layer of a Marcinkiewicz-Zygmund family, take as weights the integral over the dual family, and we get a quadrature rule. This quadrature rule is exact on the trigonometric polynomials of degree n. Okay, that's by construction. And the question is, what can I say about the error of the quadrature rule for arbitrary functions? So here is the statement. The central assumption is always, I start with a Marcinkiewicz-Zygmund family on the torus for trigonometric polynomials on the torus. I know the condition number, and I have constructed an associated sequence of quadrature rules. Now, if f is in the Sobolev space with smoothness sigma, then the integral of f over the torus minus the result of the quadrature rule is again bounded by n, degree of the polynomial, to the power negative sigma plus 1/2. So the higher the smoothness, the better is the approximation. So this is the typical error estimate that you would get for smooth functions. Again, the constant is quite explicit. It's the Sobolev norm, is the absolute constant, and it's basically the square root of the condition number. If you start with an analytic function on a strip of width rho naught, then the decay, the error rate, asymptotic decay is exponential with decay coefficient rho. Okay, so what we have seen so far is that once you have a Marcinkiewicz-Zygmund family, you have automatically approximation theorems, and you have quadrature rules. And for the proof of the quadrature rule, just to say one word, if I want to estimate the difference between the correct integral and the quadrature, I notice that on trigonometric polynomials of degree n, the quadrature rule is exact. So the integral over the projection of f and the quadrature of the projection of f are identical. So these terms here are identical, are equal. So if I stick in the orthogonal projection, I get the integral over the difference of f minus orthogonal projection and the quadrature of f minus projection. And here we know what the error estimate is, and here we can also estimate the error. So by taking supremum or whatever. So in this case, note I only need the approximation of f by a trigonometric polynomial of degree n. The only place where the Marcinkiewicz-Zygmund family comes in is in the construction of the quadrature rule. So here are a few few remarks. When you are deep inside this business and then you will see that usually the error estimates for the quadrature and for the approximation are given in terms of some kind of mesh size or a covering radius. How large a radius? So what's the largest distance to the nearest neighbor, or what size of balls will cover, centered at the sampling points, will cover everything. Now, in this case, the error estimate is a bit simpler. It's just by the condition number of the Marcinkiewicz-Zygmund family. Second remark, if you look at the literature, usually quadrature rules are related to Marcinkiewicz-Zygmund inequalities with respect to the L1 norm. I haven't seen much about quadrature rules that are derived from Marcinkiewicz-Zygmund families in the L2 norm. This is one of them. It's probably not that well known. If you check in the numerical literature, there are quadratures of this type. They go under the name least square quadrature. Say the reference I know of is Dan Heubrechts. And third remark, well, let's go back to recall how we got the weights. We take a dual system that guarantees recovery. If we use a little bit of frame theory, we could take the canonical dual frame, but for every dual system, by integrating the functions, I get corresponding weight. If I take canonical dual system, then I can say something about the particular weights. The weights coming from the canonical system are uniquely determined by the fact that their weighted L2 sum is minimal. So if you have any other exact quadrature rule on trigonometric polynomials of degree n, then the corresponding weights are the L2 norm with respect to these adaptive weights for the sampling inequality. Their L2 norm must be greater than the L2 norm of the weights that I showed you how to construct. So this is a particular property of this quadrature rule. Okay, so in a way, that's the message. If you're interested in discretization, in approximation of functions from samples, quadrature rules, this key concept from which everything follows is the Marcinkiewicz-Zygmund family. And in the second part of the talk, I want to show you which ideas go into the proof. So let me recall again. I have a smooth function, Sobolev smooth of smoothness sigma. The Pn, I'll display it again in the next slide, is the trigonometric polynomial of degree n that approximates the given sample of f best in the nth layer. And I want to get an error estimate between f and this trigonometric polynomial. So the first step is straightforward. I estimate the difference. In order to estimate the difference, I stick in the orthogonal projection. So this is the best approximation by a trigonometric polynomial of degree n. So I stick in the orthogonal projection of f, or if you want, the partial sum. And I have this orthogonal decomposition. Both the Pn lowercase and the orthogonal projection are trigonometric polynomials of degree n. And f minus Pnf is orthogonal. So this is an orthogonal decomposition. Now, this here, that's an easy estimate. The error of f minus orthogonal projection is of the order n to the negative 2 sigma plus 1. So the square of it, so n to the negative sigma plus 1/2, if it's just a 2 norm. So this is settled, and we have to deal with this part. That's the interesting part, because here, this is where we finally have to deal with the fact that the polynomial is a least square solution to a least square problem, and that the information given are the samples. So here is once again the reminder: the Pn is the unique trigonometric polynomial of degree n that approximates the samples of f in the nth layer best possible in the discrete L2 norm. Now let's see how we build up that problem. If you take an arbitrary trigonometric polynomial of degree n, and I take its value at a point xk, then it's this here. Sum over the exponentials evaluated xk, and then come the Fourier coefficients of the trigonometric polynomial. So I'll write that as in terms of matrices and vectors. So the vector of all samples is y. The vector of the Fourier coefficients of the trigonometric polynomials is p hat, and the matrix here is u. This is actually a van der Monde matrix, and you have all the numerical tools you want to deal with it. Okay. So next, make it a bit more complicated. We always do that for every layer in order to get the asymptotic rates. So now I have sample polynomial of degree n. Okay. At the nth layer, I put in the weights, and I write that as a matrix vector equation. So the vector of samples is yn. The underlying matrix, again, it's a van der Monde matrix I call u sub n, and the Fourier coefficients I call p hat. And the n indicates that I'm in the nth layer with trigonometric polynomials of degree n. So first observation, assume you are given a Marcinkiewicz-Zygmund family. So the sampling process is described by this van der Monde matrix u sub n. I look at, well, when I look at it numerically, I look at normal equations. So I look at the matrix u sub n star un. This matrix I call T. And the spectrum, so this is now a positive definite matrix. And the spectrum of this matrix is always contained in the interval AB, AB being the constants in the Marcinkiewicz-Zygmund inequality. That's fact one. And the proof is, well, it's just language. If I look at the sampled energy, let's go back here. Here, this, so the two norm of the samples is just yn, and this is un applied to vn. So let's see here. So the samples are un applied to p hat, and the two norm is just the inner product. Now, if you bring that over, you have the matrix T sub n applied to the coefficient vector. And by assumption, this is bounded below by A times the two norm of P, which is the two norm of the coefficient vector. So this means that same for the upper bound. So this means these matrices, T sub n, have a uniform spectrum with bounds A and B, and these bounds come from the assumption Marcinkiewicz-Zygmund family. Secondly, if I look at the corresponding least square problem, I solve the normal equations, and I can write down the coefficient vector. Okay, let's go back once more. If I want to recover, so if I want to recover these coefficients, then basically I look at the normal equation. So I write, oops, so that's not good. So un star on both sides. and then I take the inverse of this. Okay, so I solve the normal equation. Maybe not. It is a good way to do that. And the solution to the least square problem is a trigonometric polynomial, and its coefficient vector an, is given by this expression. It comes from the normal equations, and what's written here is the pseudo-inverse. Everything is well defined because we have checked the spectrum of these matrices. By the way, this matrix Tn is a Toeplitz matrix, and that yields numerical solvers of, say, complexity n log n in dimension 1. In Chemnitz, this is, by the way, known as the non-uniform FFT, and it has gained a lot of prominence, this way of approaching the sampling problem. Okay, so let's come to the main point. So we have a function f. We look at the nth partial sum, and these are the Fourier coefficients of f from negative n to n. We have the trigonometric polynomial Pn that solves the least square problem, and in Pn is all information about the samples of f. We have a formula for that. Now, so what we want to calculate or estimate is the difference of the orthogonal projection of f minus the polynomial of degree n that uses the samples of f and gives the best approximation. So these are functions. We go to the Fourier coefficients. So we get the Fourier coefficients of f from negative n to n, and here we get the coefficients of the best approximating trigonometric polynomial. Next step, let's write down the formula for the coefficients an. Here it is. Just copy it. Next line, I pull out this matrix. So that's the pseudo-inverse of the van der Monde matrix. So I pull it out. In order to get the identity here, I write the un. So this is the identity matrix applied to fn. That's fine. And with a yn, I have the solution. I have this inverse matrix un. Okay, so this is yn. I haven't changed anything. I've just used the invertibility. And in the next step, I use the fact that the spectrum of Tn is bounded between A and B, independent of n. So Tn inverse is bounded by A inverse squared. The norm of Tn is B, so the norm of un star, no, the norm is Tn is B, the norm of un star is also B. So I get constants that come from the spectrum of these matrices, which ultimately come from the assumptions on the Marcinkiewicz-Zygmund family. So doing this, I'm left with an expression here. So these are some sequences. If you do, all we do here is very natural. And so once we have, so here we have to ask, okay, what is that? So let's make the computation. So the UN is the van der Monde matrix. I have the weights here. Here is the van der Monde matrix applied to the Fourier coefficients of the orthogonal projections. So these are the n Fourier coefficients of f. Okay, so what I see is this is actually the orthogonal projection of f evaluated at the samples of the nth layer of the Marcinkiewicz-Zygmund family. So the kth entry of this vector is nothing but the value of the orthogonal projection at the point x and k in the nth layer. So if I take the 2 norm of this difference, I obtain the values of the orthogonal projection, the nth layer, minus, well, the yn, that was the input vector that came from the samples of f. So this is the original information that I use. So this is something I can handle because if F is smooth in the Sobolev space, then I just estimate this by the supremum norm squared. Okay, and we have seen that F minus the orthogonal projection of F to polynomials of degree n in the supremum norm is less than or equal to some precisely specified constant times n to the negative 2 sigma plus 1. This is the initial lemma that basically is an exercise of a few lines. Okay, so here I didn't write down the precise constants, but I hope that I have convinced you that as long as you use L2 norm, this is fairly easy, and we have not used any sophisticated mathematics for that. And this is in a nutshell the proof of the approximation theorem. So part 3, I have shown you a simple case where periodic functions, the underlying set was a torus, and I have shown you an approximation theorem and a quadrature rule. So this is the case we have looked at. And now let's just translate everything and generalize everything. So that's a favorite game. So instead of the Fourier basis, we take an orthonormal basis on some manifold with a measure or on some subset of RD with a big measure. We have to impose some conditions on this orthonormal basis. For example, we want it to consist of continuous functions so that we can actually sample the orthonormal basis. Now, the Fourier coefficients on the torus, well, we replace them by the Fourier coefficients with respect to the given orthonormal basis. On the torus, we defined the Sobolev space basically by weights. They were powers of the index k. In the general situation, we just take an increasing sequence of numbers, non-negative numbers, that diverge to infinity. Okay, no assumptions, just an increasing non-negative sequence of non-negative numbers going to infinity. With that, we can actually define a suitable Sobolev space by taking a weighted L2 sum of the Fourier coefficients, and the weights are given by these numbers. And trigonometric polynomials on the torus are replaced by a hierarchy of finite dimensional subspaces, which I call Pn. And I will say these are polynomials. And these are just the truncations of the orthonormal expansions to all numbers that are less than or equal to n. Okay, so you could say this is a corresponding concept of bandwidth. You could say these are corresponding concept of trigonometric polynomials. Anyway, this is a meaningful definition, and these subspaces are finite dimensional because the lambda k diverge to infinity. In some papers, say by Filbier and Mashkar, these are called diffusion polynomials because underlying they have heat kernel estimates and whatnot. So this is perfectly abstract. I haven't made any assumptions, but what we're going to think of is, of course, that these numbers lambda sub k are the eigenvalues of some natural operator on M. Usually you would take the Laplacian or Laplace-Beltrami on the manifold. But you could take anything else that you like and check. So now we have a sort of a general framework, orthonormal basis, a sequence of eigenvalues, canonically associated Sobolev spaces, and canonically associated polynomials. So in that setting, we have, well, everything is now just do a copy and paste. I take points now in the set M, manifold or subset of Rn, and I define a Marcinkiewicz-Zygmund family as a set of sampling points that yield a hierarchy of sampling inequalities for the appropriate finite dimensional subspaces, which I call polynomials of degree n. Again, if I'm given a function on M continuous and the samples on the nth layer, I can try to approximate these samples by a polynomial of degree n, so to speak, and solve the least squares problem. So nothing changes. And I can prove the same result. Assume we have a Marcinkiewicz-Zygmund family on a set manifold M. Condition number is B over A. I have associated weights T. Then membership of F in a Sobolev space of smoothness sigma implies an error approximation of F from the samples in the nth layer, and the error estimate looks exactly the same as before. I have sort of an error term. I have the Sobolev norm of F, and I have the condition number of the Marcinkiewicz-Zygmund family. Okay, you will say, but there are, I don't know what is the error term, and there is an important restriction here. Maybe I should do that in red. So I have a critical index, which on the torus was simple to determine. It was 1/2, and you could say it's related to Sobolev embedding. And also I have to think about what is how do I express the asymptotic rate? So the formula is written here. I take the orthonormal basis of basis functions whose corresponding eigenvalue exceeds the degree n. I take the inverse weight. I sum everything and take the supremum over all x. So this is the error term that comes in. If you take the case of trigonometric polynomials, Fourier basis, then of course this is just 1. And here you have k squared. And you get exactly the n to the negative sigma half. In this case, it's just something that depends on the orthonormal basis. And we have to look at that a bit more. But anyway, just with this notation, I have an approximation theorem for given f from its samples. And the nice thing is, there's nothing to do. The proof is really identical to what I have shown you before. But now we're in a completely different level of generality, arbitrary orthonormal basis, arbitrary sequence of eigenvalues. So what I showed you before, there's no work left to do. Just copy and paste and maybe adapt the notation a little bit. Okay, let's see. I emphasized the hierarchy. So you have Marcinkiewicz-Zygmund family means you have a hierarchy of sampling inequalities, and that of course gives you the asymptotic approximation rates. But you could do that just, you have a sampling inequality for a finite dimensional space, subspace. You sample, you solve the corresponding lead. You sample F, you find the best approximation of these samples by a function in your finite dimensional space. And you ask what's the error? Then the error between F and this least squares approximation is bounded by constant is a condition number, and the error is f minus orthogonal projection in the supremum norm. So sometimes you just want to do that on a single level. So I mentioned that. So question, is everything perfect now? Can we stop? Well, so far this might be a completely empty theorem, except for a few special cases like trigonometric polynomials in certain dimension. So the analysis starts to become interesting when we ask, okay, what is the critical value? There's a critical density above which, critical smoothness above which the theorem works. The formula for the error is just something that involves the orthonormal basis. So the question is, can we say a bit more? And yes, you can. Here's an assumption that gives us, that requires a bit more on the orthonormal basis. So you take all basis functions up to height or eigenvalue n, and take the L2 sum for fixed x. And only after that, you take the supremum over x. Now, if this function grows polynomially, grows like n to the d, this is an assumption, okay? If you can show that this function grows like n to the d as n increases, then the critical index, the critical smoothness is at most d half, this d here, okay? And the error function is actually n to the negative sigma plus d half. This should remind you of something. The d half is in a way the exponent you have for Sobolev embedding, say, of something in dimension d. And this is then the natural error term. And I have plenty of examples. You could take the Laplacian on some bounded domain in Rd with, I guess, Dirichlet boundary conditions. You could take the Laplace Beltrami operator on a compact Riemann manifold, and there you have, that is known that this assumption is satisfied. Now, two remarks. In this, to verify this assumption this is so much deeper than anything I told you. In partial differential operators, this is called the spectral function, and the theorems to that say the spectral function of let's say an elliptic pseudo-differential, an elliptic differential operator grows like n to the d. They go back to Gording, I think even to Hermann Weyl, Gording, but I think the decisive result is by Hermann Weyl. So the interesting mathematics comes in here to verify that this assumption is satisfied. So in PDE, this is the spectral function. If you think of orthogonal polynomials, then the inverse of this is called the Christoffel function. Again, a central object in the study of orthogonal polynomials. So this assumption is in a way natural, and I should say I didn't discover it. Tomorrow in Albert Cohen's talk, you will see that this function plays an important role in finding optimal sampling strategies. And if you look at the work of Filbier and Mashkar, they also make this assumption in their analysis of sampling and reconstruction in very, very abstract spaces. I think they show that this is equivalent to heat kernel estimates. So this is a very natural assumption on the orthonormal basis, on the underlying orthonormal basis. And this offers connections to various fields of mathematics. My message is that if you start with a reasonable orthonormal basis for which you have a handle on the spectral function, then everything that I said before applies. You get approximation theorems and quadrature rules. So here I could also take an exit, but that's the end of the sort of elementary presentation. What I tried to get across is the fact that no matter whether you try to discretize norms, whether you try to approximate functions from samples, or whether you investigate quadrature rules, in all cases, the central object is Marcinkiewicz-Zygmund families. As soon as you have constructed a Marcinkiewicz-Zygmund family, you're in business. You get approximation theorems and quadrature rules for free. So, of course, that's could say it's kind of folklore, and you always find these concepts: sampling, Marcinkiewicz-Zygmund family, quadrature rule, approximation in the same paper. The emphasis here is that you can really systematically derive what you want once a Marcinkiewicz-Zygmund family is given. So now when you talk about Marcinkiewicz-Zygmund families, there's a good opportunity to insult everybody by neglect. There are many different areas in analysis that study these objects. For example, Marcinkiewicz-Zygmund families on the torus have been studied in approximation theory deeply in connection with orthogonal polynomials. I just mentioned Lubinsky, Mastroianni, Totik. I actually turned out that I proved Marcinkiewicz-Zygmund inequalities as early as 1992, although I didn't know that this is what it was about. For me, it was simply sampling of band-limited functions and discrete models for that. What I think is very important is that you can almost characterize Marcinkiewicz-Zygmund families on the torus by means of a kind of Boiling density. So it's just counting points in small neighborhoods and taking some asymptotic quantity almost characterizes Marcinkiewicz-Zygmund families on the torus. So this basically supersedes most of the explicit constructions that have been there before. Then, so there was the phase when the torus was the favorite object. Then the next phase is sphere, whole business of quadrature rules on the sphere. Marcinkiewicz-Zygmund families were constructed explicitly, again, by the people in Barcelona, Jordi Marzo and Brignani. Quadrature rules, okay, there are many names I want to mention. And at some point, it became clear that you can play this game on much more general structures. Favorite object would be, say, Riemannian, compact Riemannian manifolds. And so the work I'm aware of is by Frank Filbier and Hrusikesh Mashkar, where they construct in incredible generality such objects. But again, there are so many constants that you don't really know what it means. So they prove the existence. But at least for compact Riemannian manifolds, again, do you know what the optimal results should be? There are necessary density conditions that are again due to Joaquim Ortega-Cerda and Brignani. So I think it's open at this time whether you can construct Marcinkiewicz-Zygmund families that are close to the necessary density. I mean, there's no information in the constructive proofs. They're just dense enough. You sample densely enough, and that's it. But whether that's a good or not so good result is completely open. this workshop is heavily devoted to random constructions, and I think I can refer to the talks this week by Albert, by Volodia, Timo Ulrich, Timo or Mario Ulrich, don't know. So let's see. Do I have time or should I stop here?
You have 5 minutes.
Okay. Okay, so now you could say, okay, that's all fine, but I have omitted the main problem. So how do you construct Marcinkiewicz-Zygmund families? I mean, that's actually what's the real question. And what I point out is just the real question is how to construct Marcinkiewicz-Zygmund families. So I found a niche there where we have been working a little bit in the last year or so with Joaquim Ortega-Cerda. And that would be Marcinkiewicz-Zygmund families for polynomials, but in complex analysis. So if you take polynomials of one variable in the complex plane, and if you take the closure, then you'll get the family of analytic functions. So if we take it very simple, we take Bergman space. This is the space of all analytic functions on the unit disk, and the norm is the L2 norm with respect to area measure. And I'm interested in Marcinkiewicz-Zygmund families for the polynomials of degree n inside Bergman space. Now, you have the full Bergman space, and you can ask about sampling sets in full Bergman space. Okay, so the sampled 2 norm in Bergman space is equivalent to the 2 norm. Okay, so we have Marcinkiewicz-Zygmund families where we do that for polynomials, where we require that only for polynomials of degree n, and we have sampling sets for the full space. And it turns out that in many situations, there is a connection between sampling sets for the full space and Marcinkiewicz-Zygmund families for the polynomials. And that's what we found, the following. So let's assume that X is a sampling set for the full space, for Bergman space. Okay, once more, this means I have a sampling inequality that holds for all functions in Bergman space. If you restrict the samples to balls, to disks of suitable radius, namely radius 1 minus gamma over n, so this means you delete a piece of the boundary, a piece at infinity of width 1 over n. The gamma should be small enough, so there is some parameter involved that you have to fine-tune. Then this restricted set X sub n, so all points of the sampling set inside a disk of radius 1 over n, these form a Marcinkiewicz-Zygmund family for the polynomials of degree n. Okay, so this means that the sampling inequality, so here you would take X sub n, samples only in X sub n, and this holds for polynomials in Pn. Okay. So sampling implies the existence of Marcinkiewicz-Zygmund families polynomial. Conversely, assume I have a Marcinkiewicz-Zygmund family for Bergman space, then I can construct a sampling set for Bergman space by taking a weak limit of these sets. So this is a concept, I think, introduced by Berling. A weak limit of sets means that this the xn converge in the Hausdorff distance is in the Hausdorff metric for compact sets to X. Okay, the restriction to any compact disk. So these are finitely many points, and they converge to the points in the limit set. Or in other words, every point in here, for every point in here, I have a subsequence in xn that converges to point here. Okay, so every weak limit of a Marcinkiewicz-Zygmund family is a sampling set for Bergman space. So now there are two facets to it. The sampling sets in Bergman space are completely characterized by Christian Seip and a suitable density. So we don't have to solve that. So this theorem, this is a deep theorem by Christian Seip, automatically yields the existence of Marcinkiewicz-Zygmund families. On the other hand, so that's where we are. But we could also see it the opposite way. If I'm able to construct Marcinkiewicz-Zygmund families, then I get as a byproduct sampling theorems for an infinite dimensional space. So this is a way of proving sampling theorems in infinite dimensions that has been useful, say, for Paley-Wiener space. You could use it for Bergman space, and I think this is a direction that's not yet completely developed. I know of 2 or 3 theorems where you construct sampling theorems from Marcinkiewicz-Zygmund families. So that would be another aspect of Marcinkiewicz-Zygmund families. So there's a completely different situation in Hardy space, which I'm going to omit. And I think I can summarize simply by saying, if you want to understand approximation theorems from samples or quadrature rules, then you should study and construct Marcinkiewicz-Zygmund families. That's it. Thank you.
Thank you very much, Charlie. And so now it's time for questions and discussions. Are there any questions and comments? Please go ahead. Anatoly, do you want to ask a question? Okay, then let me ask one question. As I understand, and this is kind of a natural way, now that you study this one very specific way of building, for instance, recovery operator, what is approximation in your case, that in this way is the weighted least squares method. But for instance, if you take the Sobolev classes which you mentioned, this H sigma, then this method, if you apply like you did with trigonometric polynomials, it gives us the recovery rate n to the minus sigma plus 1/2. But it is known that if you use very classical, very standard, just interpolation operators, then you do not lose that 1/2. You get n to the negative sigma. So in that sense, this your final recommendation. It's very, I would say, interesting one, that to go through Marcinkiewicz-Zygmund. I would say that sometimes to get Marcinkiewicz-Zygmund right form of the Marcinkiewicz-Zygmund inequality, so as we call this sampling discretization theorems, it's a very difficult problem. Sometimes it's even more difficult than others. So like, for instance, quadrature rules. So could you just comment on that a little bit more?
Well, thank you. I was not consciously cheating, but I wanted to say that the method is too simple. And basically what I have used is information on the spectral function or the Christoffel function only on the diagonal. If you impose additional assumptions that amount to behavior off diagonal, then you can omit the 1/2 or the d/2. And that's in a fairly abstract setting that, or in fairly general setting that has been done in a paper by Brandolini, Groechenig, that I had on my slides. So the price for simplicity is exactly that extra factor. And say in the context of this method, I would say it's because I only use information, or assume only information on the diagonal of the Christoffel function, and don't impose any off-diagonal decay. So if you take eigenfunctions of the Laplacian, then you have information about the off-diagonal decay, and things become more complicated, but you can prove the sharp result that you mentioned.
But for instance, let's return back to trigonometric polynomials. These trigonometric polynomials, if you go through trigonometric polynomials, the periodic Sobolev classes, then how you're gonna get that from the least squares? This, like your proof and many other proofs, they go through L infinity. But if you do approximation in L infinity using trigonometric polynomials, then you will lose 1/2 for sure. There is no way to go around.
Well, I personally will lose 1/2 for sure. I have tried.
Yeah.
But
yeah, everybody will lose. It's known.
Okay.
I mean, the best approximation of those classes, I mean, the Sobolev classes, which are defined in L2,
sigma.
in L infinity, you're losing 1/2. I mean, there's no way. Yeah, so this will be. Yeah, but anyway, other questions? Yeah, I think the whole these things to understand and the interplay between different methods is a very, very interesting topic. And I would say my personal feeling and experience that before very recently, people concentrated on the specific methods, like I just mentioned, like for instance, recovery methods based on, like for instance, interpolation operators on some kernels or whatever. But rather recently, people understood that these least squares might be good, sometimes even better. So I think this is very interesting direction to understand it well. Yeah. Thank you, Charlie. Other questions? Yeah, Mario wants to ask a question.
Yeah, just about the off-diagonal terms you've mentioned. Can you say some more words about that? Because my feeling was that not the diagonal terms are the problem. The problem with the Christoffel function is just that it does not depend on the infinite many other basis vectors, right? Which might contain quite a lot of information. But do you know some approaches that you really only take the first n and then you somehow use off-diagonal terms to do something?
I don't think I can say anything meaningful. I can only refer you to a paper by Brandolini, Groechenig, 4 or 5 authors. And they have looked at that actually on Riemannian manifolds, where you have more information about the orthonormal basis. And I think they call the kernel of the orthogonal projection with the weights, the generalized Bessel kernel. And they have information on the off-diagonal decay that gives them the optimal approximation rate.
Yeah, so this is clearly
I cannot compete with
that.
that.
Difficult to dig in all these details. It's kind of, yeah. Yeah. Okay, thank you. Other questions? Okay, if there is no other questions, let's thank the speaker. Thank you, Charlie. And so we have, we have 6 minutes for the break. And then the next talk will be by Mario Ulrich. So we have 6 minutes to stretch our legs.
Thank you. Bye-bye.
Thank you, Charlie.